Professor Dave again. Let's run a column.
He knows a lot about the science stuff. Professor Dave explains.
When we do chemistry in the lab, it's never as neat and tidy as it is on paper. Any reaction will have unwanted side products, unreacted starting material, and other impurities in the product mixture. We need a way to separate everything so that we can isolate the desired product. And oftentimes, that way is column chromatography. In the previous tutorial, we learned about thin layer chromatography, and a column will operate by precisely the same principles. So if you haven't seen that tutorial yet, absolutely make sure to watch that one first. If you're up to speed on the general principles, let's go ahead and see what a column is all about. As we said, in the laboratory, things are complicated. We might run a reaction, quench it via aqueous acidic workup to neutralize any ions in solution, and perform an extraction to isolate the organic layer. In that organic layer is your target molecule, but also other stuff, depending on the nature of the reaction. But we don't want that other stuff. We want just the target molecule, so we can get a nice clean NMR spectrum and make sure we've got what we think we do, and possibly go on to the next step in a synthesis. The way we will do this is column chromatography. As we said, this works just like TLC in that we will use a silica gel to act as a stationary phase, and then the components will separate as they move through the column based on how they interact with the hydroxyl groups in the gel. The only difference is that instead of moving up a plate, they move down the column. And we don't just separate a little bit. We put all of our material in there and do it all at once. Let's go over the basics for setting these up. First, at the bottom of the column, we place a little cotton plug using a wire. Not too much, or the column will drain too slowly, just enough to make sure silica will not fall out. Then we clamp the column in place and add a layer of sand to fill the curved bottom section. Next, we fill up the column about a third of the way with our solvent system, which is sometimes called eluent. This is the solvent system we selected by TLC, the one that gives us the optimum separation of the components in the mixture. Ideally, we can identify our target molecule by assessing its polarity and comparing this to the RF values on the plate. This will help us know what's happening to our desired compound as we run the column. Now we take a beaker of our solvent and pour in the dry silica gel, which is a powder, making sure to do this in a hood so as not to inhale the silica. Stir things up until we get a slurry, and this will act as the stationary phase in our column. It's a little tricky, but use a spatula to get it in the column, adding more solvent to the beaker as you go if necessary. Use something to tap gently on the side of the column until all the silica settles at the bottom, and use a pipette to rinse the sides with eluent to make sure it all gets down there. Start letting the column drip into a flask to help the silica settle, but don't let the solvent level run below the top of the silica. Pushing compressed air through a tube fitted with a stopper at the top of the column can help things go faster during this stage or any other stage during the separation if it seems necessary. While packing the column, use more solvent if you need to. We just need the stationary phase packed down tightly. It is very important that the stationary phase is completely smooth. There can be no cracks or uneven sections. Once that's all set, we place another layer of sand on top of the column and then allow the solvent to drip until it sits just between the sand and the stationary phase without going below. Now we are ready to load the column. We take our isolated mixture and we dissolve it in the absolute smallest amount of solvent possible that will enable us to pipette it onto the column, just a few drops if possible. While getting it in there, try not to get any of it on the sides of the column. We really want it to drip down directly onto the sand. We can then drain just a little bit of solvent so that the mixture will move through the sand and just enter the stationary phase, so it sits just below the sand in a nice even band. Make sure the solvent level lowers just enough that none of the mixture is left behind in the sand, or this part will not separate properly, as anything that is not loaded onto the stationary phase will become very dilute once solvent is added, and therefore impossible to separate. We need our sample to be very concentrated in a thin band at the top of the stationary phase for separation to work. Now we add the solvent. At first, we have to carefully pipette the solvent into the column, squirting it onto the sides at the top so that it gently flows down. We do not want to disturb the sand or the gel whatsoever. Do this until the solvent level is several inches above the sand. At this point, you can carefully pour in more solvent from a beaker. Just continue to ensure that the sand is not disturbed. And in general, once we begin to run the column, never ever let the solvent level go below the sand, or the stationary phase will dry out and crack. The solvent level should always be well above the sand, so monitor and add more as necessary. Now the sample is loaded and we are ready to start. Let the column start to drip, and we will collect in a series of small flasks, each of which is referred to as a fraction. We don't have to be too careful with the first fraction, because we know that our sample is still way up at the top of the column, and none of the components will travel faster than the solvent. But depending on how polar the solvent system is, we will soon want to pay a bit more attention. As we push eluent through the column, the components will begin to move with it and separate as they go, just like what happens on a TLC plate. Try to find an optimal flow rate. We can't go too fast or too slow, or it will not separate properly. Just a few drops per second should be fine. Often we can clearly see bands of different colors moving down the stationary phase, and that makes things nice and easy, as we will know when to be more careful with our fractions. When it looks like we are collecting organic material, we want to get fractions of a smaller volume, maybe 10 milliliters or even less, to maximize our chances of a clean separation. We can gauge the concentration by color, but don't be afraid to collect lots of fractions if you need to. Even up to 20 or 30 is no problem, provided you have enough flasks to do so. Keep adding more eluent and pushing it through until you're confident you've collected everything you need, and then you can push the rest out and let it go dry. Sometimes the nature of the eluent can be modified as you go. It's not uncommon to utilize a gradient of polarity, starting with a less polar solvent system to gently kick things off, and gradually increase the polarity throughout the course of the column, especially if you think you've collected the relevant fractions and you want to get what's left out of there more rapidly. But one way or another, now we've got our fractions, and it's time to analyze them. We will do this by TLC, so make that pencil mark, add 5 to 10 vertical notches to each plate, and number them so that you know which fractions they correspond to. Each line gets a spot from the corresponding fraction, and then develop the plates. As we said, hopefully we know which spot represents our desired product, based on its polarity compared with anything else that might be in there. Unreacted starting material, predicted side products, or what have you. If you know which one it is, then all you have to do is take all of the fractions that gave TLC data showing only that spot and no others and combine them. That's why we want to use very small fractions right when we think our product is exiting the column, because there could be fractions on either side that contain our product along with something else. And we want to minimize the amount of product that we have to throw away due to impurity, because we don't want anything else to be collected, only our target. Combine all the winning fractions in a flask suitable for a rotovap. Evaporate the solvent away, and there you have your product, purified and isolated. Now you're ready to get an NMR spectrum and know for sure if your reaction went as planned. So that's a basic introduction to column chromatography. It may seem complicated, and to be honest, it definitely can be, and your first column will probably go very poorly. But don't get discouraged. Learn by watching more experienced lab mates, practice, and soon it will seem like a trivial and mundane task. Now with extraction and chromatography under your belt, you've got a few of the quintessential organic chemistry techniques down. So let's go ahead and learn one more. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.